of Velco, and Mr. Chris Root, who is the CEO of Velco, Vermont company here in New England. And I think for a long time, Velco has been sort of very innovative, but now with the renewables and so forth, this is what you will be telling us about, what are both the opportunities and challenges of what you have done. I just also want to mention for the audience that Chris has been unbelievably proactive in outreach, in working with different societies, both European, SIGRE, and international IEEE, many functions, trying to sort of set up the vision for where the field is going, what are the realities and what are opportunities and challenges. So I very much look forward to listening, Chris, to what you have to share with us. And then we'll go like 45, 50 minutes, as Chris said, and then we'll have opportunity to ask questions. If there are some very clarifying questions, just please raise your hand, and Dan and I will look for it. But just clarifying, we don't want to interrupt too much.
Great.
Please, Chris, welcome.
Okay. Well, thank you very much. Thank you for inviting me. I'm always happy to talk about things. I'm going to pull some slides that I'm going to use, and I have sent them to Dan and Maria. So if you guys you would like to use them, you certainly can. There is data in there that is, I think, you'll find interesting. Let's see if I can do this. Yep, there we go. I'm assuming you can see my slides now.
Yes.
Okay, so I'm going to talk about reliability from a power systems point of view. I'm going to talk macro and then a little bit a micro, both. But I am going to talk from a New England perspective. So the 6 states in the United States, in the New England states, they operate their power system as one under the independent system operator located in Holyoke, Massachusetts. The operations and the planning of New England is done regionally between the 6 states. So I thought so I just want to set that stage. Velco, which I'll talk about in a minute, is a transmission company, transmission owner in the state of Vermont, in one of the states. We own all the transmission here. But I want to talk just generally. So here's a spot question for you. What do you think the percentage of generation today in New England is made up of? So this is public information that you can get through the ISO website. Today, we are now generating electricity 76% natural gas. 3/4 of all the electricity being used that isn't behind the meter solar, which actually up here is still foggy and cloudy, so we haven't burned off yet, is being generated by natural gas as we speak. 12% nuclear. Now, to be honest, part of that is because one of the nuclear units is off for maintenance, but still, we typically all summer have been running between 60 and 70%, and today it's 76% natural gas, totally dependent on a carbon-based fuel. So although people talk a lot, for example, today renewables is about 7% of our electric generation today. So a lot of talk, a lot of change coming, So if you're thinking if we think we're going to get the 76 number down to 15 or less over the next 5 to 10 years, there's a lot of change that's going to take place. So that's what I'm going to really talk about, is what happens when you have that much change happening. And sometimes it's a little bit up out in front of the engineers. So I'll talk about my little state here. Vermont's a very small state, but you know what? It's great to do experiments in Vermont because it is small and it has got tons of renewables in it. I say that we're like Hawaii and we're in the mainland. So so we had a big nuclear plant shut down 7 years ago. That's gone. We rely pretty much almost all of our generation is small distributed solar or wind, plus we import energy from Canada and from Massachusetts in most cases. So there's very little carbon-based fuel in Vermont right now. but there still are those gas plants that are located in the other states we rely on to keep the power going through the 6 states region. So the other nice thing is, up to now, right now, the peak load in Vermont is about 1,000 megawatts. Nice round number. It's easy to deal with, right? But it's 1,000 megawatts in the summer and it's 1,000 megawatts in the winter, both about the same. Another nice thing to deal with, right? So, and it's been about constant for about 10 years. We've had a very aggressive energy efficiency program, very aggressive up here. We manage peak loads very aggressively in the state with storage right now, which I'll talk a little bit about today, and managing that to keep it at that level. But it's going to change in the future, which I will talk about today. So the peaks, though, interesting. When is your time of peaks? In the summer and in the winter? In the winter, it's always been after dark. So a winter peak in the northern states in New England typically will happen at around 6 o'clock on a very cold, still night. That's when your peak load is. And by the way, none of your solar is running then. In the summertime, it's typically at the end of a 3-day heat wave. Typically in New England, it's about between 4 and 5 o'clock in the afternoon as an aggregate 6-state region. But in Vermont, it's between 8 and 9 o'clock at night. Why is that? And I'll talk about that. That's because of our 1,000 megawatt peak, we have almost 400 megawatts of solar. So that solar is all cranking, and I'm going to show you some curves that talk about that. So we also have wind here. We have about 15% of our peak is wind, and about 12% is hydro. So we have a lot of clean generation here. We also import 225 megawatts, about 22% of our energy needs in Vermont come through Hydro-Quebec HVDC link that we have with them. That's all hydro, also clean. So now the other thing that is unique about Vermont is they were very aggressive, the largest distribution company here, in cutting a deal with Tesla. They were the first utility to cut a deal with Tesla to put Tesla power walls all through the state. So they sold Tesla power walls to customers for about $15 a month. You could lease them. They put it in a garage, and it was basically sold as an uninterruptible power supply. So you could get a day or so's worth of energy stored in this battery in your garage, and maybe you didn't need a generator. So they're small, but we have, well, it's almost up to 3,000 of them now. There's a lot of those things around, okay? So we have a lot of distributed storage. We have a lot of other storage. We actually, now we're almost up to, we have 2 more utility scale storage plants being built as we speak now, but we have 2 other big ones, but we're building more of them for that, for a lot of reasons, which I'll talk about. So that's what I do. Primarily our transmission system is a 345 kV and 115 kV, but that's not, so I wanted to give that context. So great little lab, 1,000 megawatts, winter and summer, very reliable transmission system so far. Okay, let's talk about some of the things. I wanted to mention the fact we talk about reliability and the politicians talk about the reliability of the grid. What are they talking about? So there's two definitions of 2 types of reliability. One of them, do you have enough generation to meet the load? And I'll talk about that a little bit more about that, but you need to be able to have enough, right? And you have to plan for it 3 or 4 years out to make sure you're going to have enough for this year, for every single year. That is traditional capacity reliability. It was based historically on 1 day in 10 years where you wouldn't have enough capacity. That's the kind of the risk calculation that you would do on that to make sure that you have enough generation to supply demand. It becomes much more difficult when you have renewables that are weather-based and may or may not be able to be predictable depending on the day that you need it. So that's more complicated. And I'll talk a little bit about some of the issues there. Then you have your traditional reliability was, hey, did the wires fall down? Is the power lines available? That type of thing. When you look at that combination in Texas, big deal in Texas, in February of this year, a couple things broke down. They had an ice, it was very, very cold, and they had an ice storm. So there were certain parts of Texas which had ice on the wires, so they had a problem with the distribution, reliability, deliverability. But the real major issue was that the gas transmission system, pipeline system froze up. And a lot of the gas generation in Texas was unavailable because they didn't have gas. So that was a problem. They didn't have backup sources on site. So many of the gas plants couldn't run. In addition to that, 22% of the wind power, and there's a lot of wind power in Texas, had ice on the blades and could not run. So you had reduced wind and you didn't have gas. So that was a huge issue. So huge problem. So, and at the same time, we're all going all renewable, all in. We're going all in on renewables, and that's creating a whole new set of problems that we haven't dealt with going forward. So in a lot of the historical way the power system's been run is conventional based on what we've done in the past and projecting the future. You got to throw that model out, right? Because what's done in the past isn't really going to apply necessarily in the future. In the past, our big power plants had coal piles or they had oil tanks on site. Now we're relying on gas transmission pipelines, which could go thousands of miles to bring gas to those power plants. So now you have another added reliability component that you have to worry about, which you don't control, by the way. So, how a power system works, many of you all know this, it's not a big surprise, but I always try to remind everybody of this, and students, is that, remember, you have to balance on an AC power system demand, use, and supply instantaneously, all the time, every second of the day. So that balance is so important. And we've done a good job. Every once in a while it gets out of balance and you have a big blackout. But in general, the supply and demand, and it was measured by frequency and keeping our frequency involved at 60 hertz in the United States. So is, a little bit on either side, mechanisms happen to add more generation. In the future, we're probably going to have to not only supply, managing the supply. The problem with the supply is as you're more weather dependent on the supply, and you can't change the weather, okay, you either have to supplement it with storage or you have to manage the demand. So one of the big things that's going to happen in the future is more active demand management on an aggregate level, okay? That's going to have to be done on very fast speed to be able to keep those two things in balance, because you have to keep them in balance. But the question is going to be, how many of the tools you have to manage on the supply side, which traditionally we've only managed it on the supply side, unless we get into a big problem. So now you're going to have to manage both. And that's the only way you're going to be able to keep things in balance, to be able to keep the power system in a stable format. So important, different mindset than what we've had in the past. So. All right, so now I want to show you is how's the weather impact generation. So this is a 20 megawatt solar plant right out in Vermont, central Vermont. This is, you could see this if any of you have ever skied at Okemo Mountain. This is just north of Okemo Mountain. Okay, it's a 250 acre site for 20 megawatts. So it is, this is the output, okay, over 24 hours of this plant, okay? So why is it so jagged? Because it was a beautiful, sunny, with big white clouds day. You have big white clouds that came over the sun and moved away. And look at what the output of that 20 megawatt plant did. When it had full sun, it was at 20 megawatts. It took drops very fast down to half that speed, half that output. So you have a generating plant which you don't control. It just does what it does what it's going to do. But that is a big variance, that when you're running a power system and you have lots of plants like that, if it's a partly cloudy day, you don't know when the cloud's going to come. It's almost impossible right now with technology to forecast exactly when that cloud's going to come by and then go away, right? So you have all this generation that's moving around. As you add more and more to this portfolio of in rely on this, that could be an issue, right? It is an issue. So that's why I say you have to have other ways to be able to mitigate these rapid changes that go on with that. Now, if you're in Arizona, you don't have clouds. You're in California, you don't have clouds. You go other parts of the world, but in the Northeast part of the United States, what do we have? We have snow in the wintertime coming up, by the way, all of you new to New England, but also we do have clouds, right? So we have clouds come by. So this is reality, okay? So you have to deal with that. So I thought I'd just show you that plan. Output. Now, this is a crazy output. It's called the duck curve. Some of you probably all know this. What a duck curve is, it came out of California. And basically what they said, it looks kind of like a duck. And they originally said about 5-6 years ago, oh my word, we keep adding solar in the middle of the day. And California is a north to south state. What does that mean? The sun goes down at the same time, the whole state. So what happens is all that generation of solar that's been running in California all shuts off in the same half hour. So when that shuts off in the same half hour, we don't have the capability to get enough conventional generation running in time. So we won't have a reliability collapse. So they put a lot of storage in to take that ramp rate better. They have a huge storage plan in California to basically take that ramp rate and make it not so steep. So what this chart is the duck curve in the state of Vermont. So each year going down the bottom one is 2021 this year. So what it shows, this is 24 hours a day, 24-hour day period, and it's the load. So this is actually in April. I'll be honest, I cheated. April is a light load period of time, so it makes it even my point more dramatic. Sorry, but it does. I'm making the point. So in the middle of the night, you can see in the middle of the night what the load is pretty consistently year to year. And each one of these curves is a different year, except for the top one. So each year you can see it goes down and down and down more in the middle of the day. Why is that? We keep adding solar during the day, more and more. Now, about 4 years ago, we crossed over so that in the middle of the day, in April, on a sunny day, the net load is lower in the state than it is in the middle of the night. So think about that. In the middle of the night, the load is greater than the middle of the afternoon when everyone is up and doing and using electricity. It's because of all the solar and all the behind the meter solar and rooftops and everything else that we have. It's at 380 megawatts worth of solar cranking away. Okay. So you can see how low it's going in. My prediction is in about 2 years, we're going to go negative. The state will be a net generator of all distributed. These are not big power plants. These are not, the biggest power plant that we have in solar is 20 megawatts. That's it. It isn't, we don't have 1,000 or 300 like they have in California, these big plants down south. In New England, you don't have enough land to do it. So you have a lot of small ones, right? So that's what that is. I just want to tell you right now that the top purple one is a day or two later than the bottom one. Okay, here's the sunny day at the bottom. The top one is what happens a cloudy day. Radical difference, radical difference. If you're trying to figure out what generation you need in 2 days, you better know what the weather's going to be. Is it going to be sunny and you're going to have the bottom curve load, or is it going to be cloudy and rainy and you're going to have that? That is a huge difference. And you better figure out how you're going to close that gap, right? So, so that is an important thing I just wanted to let people know. And in Vermont, and like you can see that the peak happens when all that solar turns off about 8 o'clock at night. You know, when it's done, you're basically now in conventional generation, or maybe a little bit of wind. Okay, so that's a duck curve in a small state, but it looks just like California. All right, with a lot of solar. All right, so in our state, we have some utility scale 20 megawatts, but most of it's smaller, megawatt and less, but lots of it. Lots of rooftops in Vermont. You drive around here, every school has solar on it. You have quite a bit, very much intermittent. The other thing is, as a grid operator of the transmission system, I can't see all that. I can see those aggregate numbers. I can't tell which ones are running. And we have a whole program that's going to connect 150 kW and above. And we're going to actually get outputs from that sent to us. So we're going to see when they're running, because I don't even know exactly how much is connected to each substation, which is a problem. So, and storage plays a huge role in us managing our peak loads right now in Vermont. There's a financial component to that, but storage options, we're going to go all in on storage, is my sense. So, I just thought I'd show you a picture. This is behind our office building in Rutland, Vermont. This is about 450 kW worth of solar. and we do have a 250 kW battery, which is in the bottom. At the bottom of this slide, there's a little building that has a little brown roof on it. That's our battery. We actually get a payment. We allow from Green Mountain Power, the distribution company, to control that storage device when there's peaks. So they turn it on, and they make us a payment. They run it for about 3 hours, about 2 or 3 times a month, and we get a payment for that. That payment has made that battery storage economic for us. And we charge the battery off that solar plant. So it's hugely important, because if you try to buy energy from the grid to recharge your battery, the economics are terrible. You want to be able to charge it from a renewable source that has low cost. Well, so what's going to happen in the future? So we are going all electric vehicles. We're going to go heat pumps and electric heat pumps. So in our state, we have a lot of fossil fuel generation. We do not have a lot of natural gas. People heat their homes with wood and oil and propane, right? That's how they heat their homes in Vermont. So that being the case, we want to electrify that and get it off fossil fuels. So what I'm showing you here is our summer peak forecast and our winter peak forecast for the next 20 years. This is a study that was done by us. It's in line with the ISO New England's loads. So what I'm gonna look at is the summer peak first. So the blue line is kind of a base load, business as usual, not much change. The reality of it is, if you add a lot of electric vehicles, and that's the green dotted line on the bottom of the left-hand chart, that shows the load due to electric vehicles. Now, in Massachusetts, where you're at, has a mandate for a lot of electric vehicle demand that's going to be in this same, but in this area. But it really does matter on your summer peak load how you're going to run those those charges. You have to manage the demand of those charges. You have to. You're not going to have distribution capacity to do it. You can't fast charge at 9 kW, 12 kW, 15 kW in somebody's garage and try to do that on the existing distribution system. So you have to manage them. If you look at this, the base load, which is running around 1,000 megawatts, it goes up to 400 megawatts just in the summertime, and that's based through car charging and also heat pumps running as air conditioners. So when you give somebody who doesn't have air conditioning a heat pump to do heating for a majority of the year, they're in the dead of the winter in Vermont, heat pumps are not effective, but you can do the shoulder months really well with the heat pump. But the issue is going to be in the summertime, they get free air conditioning, or they have air conditioning, not free, but they have air conditioning, which they didn't have before. Now that you're doing centralized air conditioning, it drives up your electricity demand, which is good, except if you're charging your car at the same time. So you have to really think about that, because if you don't, you're going to end up going from 1,000 megawatts to almost a 40% increase in load in 20 years. So that's a big increase. And on the winter time, it's even worse. So your heat pumps are really trying to keep up if they can, and that demand goes way up, and you're now looking at a 50% increase in demand. Now, both of these assume an active demand management program on top of this. So this is managing load as best you can, but if everyone is using these things and you need to, the electric usage rates are going to continue to go up. So these are published that we did in the Vermont System Long Range Plan we put out, and it was accepted by the regulators in Vermont in July. So these are numbers that are 2021 numbers with our forecasts that have been accepted by our regulators. Okay. So those are some of the big issues. So looking at transmission reliability issues, resilience, I love this word. And, resilience is a much bigger thing than traditional reliability. Our regulations haven't caught up with it, unfortunately, and they will, but they haven't yet. But it's so important now. If you become more dependent upon electricity to charge your car and everything else, which I'll talk about, you need to be able to put it back together after a storm faster. which means, which I'll talk, it needs some work to do that. Our cyber threats are still increasing and they're significant. The amount of money in utilities that's spent on anti-cyber attack is probably the single largest increase of any spending they do traditionally. This is our biggest increase in spending that we go. One of the big questions, the Federal Energy Regulatory Commission of the United States has put out an advance notice of proposed rulemaking. And in that, in their comments we do back today, is that, we have to change the way we finance transmission connections to renewables as one part of it, and how we get paid by that. Right now, if you want to build a renewable plant, it's on your project to pay for the transmission to it in New England. It's a little different in other parts of the country. So one of the ways that all the wind got built economically in Texas, in West Texas, was the state of Texas built a transmission line, a large capacity transmission line to Western Texas is area of where nobody lived. They built a line to nowhere and everyone built wind farms all around that and connected to it. It was social. The cost of that line was socialized between all the ratepayers in Texas. It enabled a huge amount of renewable energy to be built in this area where there typically was very low amount of electricity used. And we have similar issues in Vermont. The Northeast Kingdom of Vermont is very sparsely populated. It's got mountains and it has many, many dairy farms, and not a big user of electricity. Give you an idea, the total load in about an area that's about 20% of Vermont is only 50 megawatts, that's it. Right now, there are 500 megawatts of renewable generation in that area. The generation swamps the load. The problem is that the power system was really designed for 50 megawatts, and now you have 500 megawatts worth of generation there with many more opportunities for generation, but we can't get it out, can't be exported out, it's a limit. And right now, they won't give any more new permits from that area because there's no way to export it. So the issue is got to be something has to give. The only way you're going to get to a renewable future that you expect is to be able to finance and not have these small plants pay for this very large scale transmission cost. Same thing goes for offshore winds in Massachusetts and Rhode Island and Connecticut. There's going to have to be a fair amount. The first group of renewables is going to connect to power plants which have shut down, the coal power plants that were in Southeast Massachusetts have shut down. They have beautiful substations. In my old company I worked for, I built a beautiful 345 gas insulated substation around 2010. It's gorgeous. There's no load there because the power plant shut down since then. So they're one of the plans, well, they're going to bring in a lot of the offshore wind into that substation and make sense straight on the ocean, bring the cables in there, and then that minimizes it. Eventually you run out of capacity to do that. And then you're going to have to spend a huge amount of money on reinforcing the transmission system in New England to accept large scale, beyond a couple thousand megawatts worth of wind. And that's a big deal, and who pays is the big issue, and that's going to get decided in the next year or so. On the distribution system, we have to deal with increasing distributed generation on the system, but also car charging loads in storage. And you can't have everybody. Here's my joke is this: how do you know that you and your neighbor are both charging your Tesla at the same time? Your shared transformer is on fire because it's overloaded. If you're both charging your level 2 charger at the same time, a level 2 charger is basically the same amount of load as the rest of your house. So you've doubled the load of your house. If you and your neighbor do it and 3 other people on the same distribution transformer do that, that's a problem. Okay, so you got to figure that out and make sure that not all those charges are running at the same time. That's a problem. At the same time, you have to build in storage. There's going to be more and more storage out there. We need to be smart about where we put it and how we use it. But we have to storm-proof the lines better. You can't now live 3, 4 to 5 days I ran over 70 really large storms in Massachusetts and in New England in my former life before I came to Vermont. And I'll tell you right now, we had many 5-day storms. If you're going to electrify everything, you cannot have a 5-day storm. You can't. And I'll talk about that in a minute. And in climate change, which is going to have more storms of greater impact. So this is the comparison of new versus old. In the past, the utilities would do this. If you didn't have lights for a couple of days, it was like camping. People said, oh, we don't have lights, we'll put candles on and we'll cook out and that type of thing. Well, now, and maybe we'll throw some food out, we'll play board games to that. That was old thinking. That doesn't work anymore. Now, I can't charge the car. I can't drive anywhere. Oh, that's not good. I can't, oh, no cell phone? Oh, that's a big problem too. No cell phone, no internet. How can we live without internet, right? So the dependency on electricity is greater, but we have never changed our standards. We've never told the utilities, you need to make sure that your power system can be put together faster, and we'll give you the money to do that. So that's a problem. That regulation is lagging what the future needs are going to be, okay? And your heat pumps don't work. That was a big problem in Texas. It was so cold, they didn't have electricity. They couldn't heat the houses. I have actually seen pictures of people literally taking portable ventilation tubing, running their car heaters in their car, running it out the window and running it into their house to try to heat their house by their car heaters. That's ridiculous. But that's a problem because electric heat pumps, you can't heat houses if you don't have electricity. That's a big problem. Okay, so electricity is going to become more critical to the world. And we have to think differently about what does that mean for our reliability. Either that or we're all going to have standby generators or storage or something like that. It's okay. And that may be one of the solutions, maybe a cheaper solution actually to do it. So as I'm finishing up here, say, well, I'm a doomsday person, right? I'm saying all these bad things. No, I'm an engineer and I'm seeing all the problems and trying to solve, how do I solve these problems, right? So the North America Reliability Corporation, which is responsible for the reliability in the United States and Canada, they set a lot of the rules, the regulations about reliability. They have, every 2 years, they put together a list of risks to the power system. And this slide came from Mark Larbury, who's the vice president at NERC. And this is the 4 categories of risk that they say are the biggest risk to the power system and the sub-risks in here. So they say grid transformation. That's the title of my topic. It's changing really, really fast. You're changing all your generation and where it lies. The future generation will not be in the same place as the old generation was. So you have to figure out a new planning strategy. Balancing, as I talked about, it's hard to balance those two things when the wind is changing and the sun is changing. We have more complex relay systems, and we have a lot of inverter-based issues. Inverter-based issues are going to be increasingly a problem, and having rotating inertia for the power system is really important. When you don't have rotating inertia, you have to create it or work around it. That's a problem. So that was the first one. The second one has to do with as physical, cybersecurity, electromagnetic pulse. Just as a side note, Vermont, my company, Velco, was the first one to build a data center, which is EMP proof. So we have an EMP proof building that has no capability of any electronic signals to get in and out of it. And this would be if there was a nuclear explosion, a high altitude nuclear explosion, the whole world won't work, but at least that one building, those computers in there will still there. And we have spare computers located in there in case we ever had to do it. But that's doing, and more people will be building those. They are building those now. Extreme weather, climate change is going to dictate, and I just did a study of a 40-year look ahead of what climate change could do to us. In our state, more storms, more stronger storms type thing. Some more flooding issues with us. icing conditions, those type of things are going to be important. But near the coast, the rising tides are going to be a big deal with the ocean levels. And then remember that we're dependent upon different things. In the short term, we're dependent on natural gas. We're depending on the telecom system holding up. My company here owns a completely redundant, independent fiber optic high-speed system that we run through the whole state to run the power system. We are not reliant on anybody else except ourselves now. And then we use that fiber in underserved areas to give internet connections to areas that still don't have broadband connections in rural areas, which is a little out of it. But we still dependent upon a bunch of other industries to keep the power system running. And that's what the last one is. So I thought I'd share that with you. That's a public document. Yes. I see there's all these chat things. I'm sorry. I'm going to get to those in 1 second. So this is pretty much my one of my last slides. We're building a new data center. Second one, this is our backup data center that we're building right now. It's going to look like a barn. It's going to look like a dairy barn when we're done. You're not going to know it is there. So it's going to blend in Vermont with all the dairy barns. It's going to be red with solar on it. It's going to have a bunch of solar on it, but it's going to look just like a dairy barn so that people won't know what it is. And so in ending, and I'm going to now take questions and look at things that are new generating sources that are going to happen. It's going to be harder to operate in the future because of this intermittency in weather dependency, right? So we have to get much better on predicting the weather. You have to be much more flexible in generation on how we do when you have much more non-carbon based fuels. Society, we're tying ourselves to electricity, that we better be reliable or we're going to have a problem for that. Less tolerance for outages. We already see that all the time. I say you have until the cell phone dies to get the power system back together. So, and cyber threats are definitely a national security issue, which will continue. That's not going to go away. And just changing our attitudes on it are going to be important. So with that, and I apologize right now, my screen, I'm going to take this off and I'll go back to the chat, I believe, and we can add, and I'm going to open it up to questions, but let me close down my screen and see if I can get my chat opened up. Okay. All right. So if it's okay, Maria, I'm going to look at some of these and say, I'm wondering if Vermont will plan anything. Oh.
Please do. Yeah, go ahead. Yeah.
Oh boy, they're coming in so fast. All right. How does the distribution company utilize the 2,500 Tesla Powerwalls? They can be controlled in an accurate manner. Yes, they have communications to every single one of them. And what they do is part of the reason they rent them to you for an uninterruptible power supply. So if the lights go out, you use your battery. But then they rent it to you pretty cheap, $15 a month. That's pretty cheap. But what you have to do is the utility reserves the right to empty it 3 times a year for their purposes to control peak load management. So the utilities in New England, in Vermont and all around New England, their bill on the transmission cost is dependent upon your peak load during the month. So they forecast when the peak hour is going to be. It's that last peak hour. And they look at that, and what they do is they manage that through the Tesla Powerwalls as one component of it. So they run all those, they keep their peak down for a couple of hours, okay? Typically end of the day. So they'll run that, run those down. And that's how they pay for that program, because it saves customers so much money by lowering their peak load. That's how they manage them. And you have to pay to fill it back up. That's part of the deal. It's your electricity, but it's only, they typically only do it 2 or 3 times a year, and they won't do it if a storm's coming. They will not touch it if a storm's coming. So if, you know, it's your power supply if the lights go out. So the storm's coming, they forego that. Okay.
So Chris, just to clarify that one,
yeah.
the rates, tariffs at the distribution level are not fixed, right? They are now dependent.
No, they're fixed. They are fixed. They're not time of day.
So how do you do what you just described now with the small customers?
So small customers that have one, what they do is they it's a fixed rate, right?
It's
So,
fixed rate, yeah.
yeah, so, but the aggregate demand in the utilities, aggregate peak demand sets their monthly transmission rate. So they hit all of them. So doing it at
I
a
see.
macro level.
Okay,
That's what it
okay.
is.
So you cannot differentiate between people in the neighborhoods and stuff, right?
Right. No, we don't. They hit them all.
Is there any plan for that?
There might be.
Okay,
Yes.
okay.
Yes, they could. It's just the next level of sophistication in dynamically managing load.
Yeah,
That's going to be the key thing. That's going to be the next thing.
okay. Thank you.
Climate change for extreme things like extreme heat. Yeah. Extreme weather. So like I said, Vermont has a Northern Vermont University has a big weather program. I know MIT has a weather program. We just did a backward look 20 years and a forward look 20 to 40 years. Just got the study from the weather professors and showing that the issues going on, what the climate change impacts will have for Vermont. We're not going to see huge increases in temperature here, but we are going to see more storms, more clouds, things like that is what our forecasts are. More flooding potential, ice storms, scary things. Ice storms are really scary. So those are the things that we're going to worry about. We already have cold built in. We already get wicked cold. We already get heat. So that we already factored that. That's not unusual to us, like in Texas. Tesla Powerwalls are owned by the companies, the distribution companies. You rent them from them, but you can own one. So they have a program, Vermont Power, called Bring Your Own Storage Device. Bring it on. So if you're going to use a Tesla solar system now, it's required that you get a Tesla Powerwall with it. So if you buy a solar system now from Tesla, it used to be Sunrun, so they've rebranded as Tesla. So if you get a solar system on your rooftop, you have to get a storage device with it. And that one, you can still get paid by having a storage device for if you allow them to use it for demand management. So you'll get a payment for that. You'll get a payment like we do at Velco for a bigger one, but you would get a payment for that to help pay for that storage device, as long as the utility can use it when it needs it. So yeah, that's how that works.
Great, thank you. So are there more questions?
Yeah.
Maybe Chris Lashway. Chris, maybe you want to ask yourself. I think you're unmuted. You can just ask question. Chris Lashway, or I can just read the thing.
Okay.
How do you keep the battery temperature up in the winter? What kind of parasitic losses does the heater circuit amount to? Presumably there is a trade-off in cold operation, parasitic loss, and a heater coil. This is a guy from MIT Lincoln Lab asking you, but I think he's not hearing us, so I asked him on his behalf.
No, we have heaters in that building, right? So we do have heaters in that building that have to heat it. That does reduce our winter efficiency quite a bit. I mean, it is what it is, right? So we do have to heat that building in the winter. Yeah, this is that's why it was so critical for us to have it next to a solar plant, so that we can use the energy from the solar plant. And even in the winter, although I will say one thing about solar in Vermont, we have documented that for the last 5 years that we've gone 4 days in the most 6 days with no output of solar due to snow on panels. Every single year, and usually in January, we have no output, zero, from photovoltaics due to snow, a big snowfall, and it's taken several days for the snow to melt off the panels. So you're going to count on that being there. That's a problem in the wintertime.
So another question from Lincoln Lab from Ted Blumstein. Any future increases in biomass?
So biomass, thank you for saying that. So we do have a 50 megawatt biomass plant in Burlington, Vermont right now, and it uses wood waste. We have a lot of logging in Vermont, right? So we cut down a lot of trees and replant them. And we use that wood waste to run a plant, 50 megawatts, owned by Burlington Electric Company, municipal. The issue is right now, the big debate is whether biomass, even though it's renewable, it's not carbon free. And that is a debate that everyone is waiting to see in the federal legislation, whether they allow biomass to be part of some of the tax credits and some of those type of programs. I think it's still debatable right now. My sense is that I think Bernie Sanders is going to be pushing to keep biomass in, as well as Senator Leahy. We have two very senior senators in Vermont going to try really hard to keep that in, but I just don't know what the ultimate answer is going to be on that. It's going to come from that legislation. I think it's going to either tell you whether biomass goes up or down.
So another question from University of Tennessee, Professor Yilu Liu, whom I'm sure you know. Mm-hmm. What level of EMP is the data center built to protect? Do you allow students to visit? What level of EMP, electromagnetic is the data center built to protect?
Oh, okay.
And
so
the
we
second
use.
part is, would you let students come and visit?
Well, it's probably would. It's a data center, so we have to be careful as a skater and stuff like that. Basically, and there were several papers, I think, written on this technology. Let me just talk about the data center. So it was built on a standard of the United States government standard. So it's the United States military defense standard that we use. Okay, so that's what limits it. And we tested it also to that. So the building was built with it's a cement building, all around, all six sides is cement, but in the cement is iron filings and copper filings. It's pre-mixed in the walls, and everything are built horizontally, and then they're picked up by a crane to put the walls in. So, and then you seal all around them. So you say, okay, well, that's fine for what's in there. So we have a generator backup. The generator backup building is also EMP protected. In the electric wires, the only cables that go in and out of that building that are metal that could conduce it, which are totally protected, have filters on them and chokes on them, are the generator leads. Everything else in the power system also has filters on it. All the electric leads going in, they have filters to filter out any EMP that could come from the outside. And everything else, the communication, all fiber optics going in and out of the building. So we do that. The building is made of cement with this particle filings in it. It is a new technology that was just developed by the United States of America defense industry that is being promulgated around. So I would have to find out if I could get tours of it. I don't know if I can or not. It's basically just a big cement building with filings. It has double doors. It has chokes at the doors. It's an electrical engineering, a civil engineering built to electrical engineering standards. How's that about as far as EMP chokes? There's double doors. There's chokes at every, all kinds of stuff. It's quite a engineering project.
So Chris, there are some very early questions, and I'm going to speak on them. And so there's a question from Joseph Rusnak. It asks, do you have any prediction system to predict the weather conditions, to use it for PV power control, to be able to find the appropriate answer when to product electricity and when to store it for the future?
So let me just, sorry, I'm in the sunshine here, so let me just move over. We spent a lot of money working on that problem with IBM and an IBM spinoff to be able to predict the amount of solar radiation at a 1 square kilometer mile thing at different heights, as well as wind for where the windmills are, wind turbines are. So we spent a lot of money that, and I would say the results were mixed. We can predict the next day what the weather's going to be, but to try to get it down to exactly your panels is very, very difficult, in that the weather calculation technology is not to a level that will allow you to do that. At 202, this cloud's going to be over you, and at 204, it's going to be gone. I think it is a opportunity for weather modeling to continue to grow, and I do think it's going to be funded by Department of Energy. I think there'll be funding levels for that, but you got to take your modeling of weather to the next level, which is really hard. Those of you who deal with it, it's a really hard problem to predict.
Chris, let me inject one related question there. ARPA-E has the full program now on how do you design the incentives for managing uncertainties in the market. Okay, it's called Perform, and we participate in that. Other schools and national labs participate. So in order to give incentives either to solar plants, to DRs, or to the system operator to do better predictions, you really need to convert that somehow into some longer term contracts or that insurances or whatever. Yeah. Can you give us a little bit your take on where is that going? Because even reserves, how many reserves you need, it's just all over the place.
Right. I agree. And it's going to be more important in the future. So what's a couple of things on the market. So what they're changing the market rules, so a lot more renewables coming into the market for capacity reasons. So that's going to drive the price down. So because they're going to come in and really, low prices, because their cost of ownership is lower, and there's no fuel costs, and they'll drive some of the conventional natural gas and other power plants out of business, or they're going to have to come up with another plan to keep them in reserve that they don't run very often, but when they need them, they're going to need them. And I think the market rules are going to have to change, because your point is a good one. You can sign up for all this renewable energy, tons of capacity. It looks like you got more than you ever need, but is it actually going to run on the days you need it to run? And you can't take that risk. So you have to have a backup plan, and you have to somehow figure out how to pay for that backup plan. So if you only run these generators a few hours a day, a few days a month or whatever, then you have to pay them. And it's going to be it's going to be really strange. Though the program you're mentioning is so important to be able to do that probabilistic calculation to see when you're going to have a problem.
So a technical question related to that. Do you guys feel that you have good enough software to manage uncertainties in a flexible way from the control center, or else even to manage the seams? You said Vermont is Hawaii on the mainland, but does it exchange power with the rest, and who coordinates that?
Yeah, we do all the time. We buy power from the other states, and ISO New England. So ISO New England does the market. ISO New England does the software for that stuff. I don't think, my take is they would still like to have more sophistication in terms of exactly what you're saying. Okay. ISO New England is the marketplace, and they are worried about it, to be honest. There's a lot of market rule changes that are going to take place, and they're very worried about it. Because if you're going to do it strictly on price, you're going to end up with all solar and wind projects, but that doesn't work at night. It doesn't work when the wind doesn't die. So you can't just do it on price. It can't be just market price. So that's a problem.
And I know that there are a lot of technical people here. So how relevant is to optimize voltage support in all of this?
Voltage support is hugely important. I just read, and I was going to do it if I had time to talk about this. There was just in Texas, they had a short circuit on a current transformer in a 345 kV substation in Odessa, Texas, for 3 cycles. It quit in 3 cycles. the voltage drop on the 345 was about 26% voltage drop during that
Wow.
time. Tripped off 1,200 megawatts worth of solar inverter base that was over 120 miles away. So in the 69 kV voltage dropped like 46. So 26 kV at the 3% drop related to a sub-transmission voltage drop of 46%, and they tripped off all kinds of stuff in the area. And so the issue that I have on voltage support is that all these inverters are really good and give you voltage support. You just have to figure out how to control them all. And if they're distributed, it is so hard. So you have to like almost engineer every rooftop to say, what are you going to do for bars for me? And if not, we're going to have many, many more electronic or rotating voltage support devices on the power system to do this. ISO New England, just to let you know. So what I have in my system, I have a StatCom, I have an SVC, and I have 4 synchronous condensers. All of them doing kind of similar things, right? So on dynamic voltage control and in VAR control. ISO New England's new standard, the new thing is they want any new devices like this not to be power electronics. They want synchronous condensers. This is kind of a little bit old school, rotating machine that does generation, that is online, that's doing VAR support. It's fast. It's not as fast as the electronics, but they want the rotating inertia there.
Yeah, unfortunately, we are running out of time.
Okay,
and
sorry.
now there may be some more questions. We will try to address them with Chris. And actually, some of you may want to follow up with direct questions to us, and we'll forward them to Chris. I have all sorts of questions on voltage and incentives for voltage. So, you know, very much appreciated the fact that it's not just dynamic voltage, reactive power, it's even scheduling, you know, how much you can transfer and stuff. So some of us have been working on this for a long time, but again, there are no incentives to.
Right, exactly. And those are going to, I fully believe that those incentives are coming. They're going to change. They have to. They have to. So thank you. Thank you very much.
Does President Biden and administration know about these nitty-gritty technical roadblocks? Who communicates that?
So that would be the engineering departments at NERC and in FERC. But NERC is probably the place that they're the ones who set all those reliability standards. So I would say NERC. And I do think they do know about it. They do know about it. And we had a conference call. IEEE does a lot with them, to be honest, with the administration now. DOE and IEEE FERC engineering staffs are tugged into IEEE. So you're going to hear more about this at some of the panel sessions at the general meeting at IEEE PES next summer.
Great. Thank you very much. We could use another hour, but nobody has it. Very much appreciated. And we learned a lot and hope to stay in touch.